All right, this is lesson 10.5. We're going to look at calculus. Yes, the calculus of vector valued functions. We've seen these ideas before, right? Position, velocity, acceleration. But now I want to look at it in the vector form. So if you look at the position vector, let me make this a little bit bigger. There we go. I guess we can call that position usually s, like s of t. Well, I can write that now as a vector. And its two components are the x component, which is a function of t, and the y component, which is a function of t. Okay, so what does the position vector do? It gives the location of the object. Okay, so once you have position, we've learned that we can then figure out the velocity. Yes, the velocity just happens to be, you got it, using calculus, the derivative. So we will just use the derivative of the components. So the derivative of x, which is x prime, and the derivative of y, y prime. Okay? And then there's the acceleration vector, which is a of t, and I can do that like this. It's the second derivative, right? Second derivative of x, and the second derivative of y. Okay? And then the speed, well, we know that speed is the absolute value of velocity, so it's like the magnitude of velocity in terms of vectors. So I'll just use the double bar absolute value sign. The magnitude of the vector. And yes, that is just the components. Whoa, that looks pretty ugly. Yes, the square root of the components of velocity, which would be the derivative, all squared, plus y prime of t, that's all squared. All right. Then two more things we need to know. Distance traveled, that's like the arc length, if you think about it, the distance. So yes, it's the integral from a to b of, and it's this, it's the x prime t all squared plus y prime of t all squared dt. Okay. And then the last thing I need to show you is when I say at rest, that means the velocity has to be equal to, you got it, 0. And notice in component or vector form, we need both components, the x and the y, to be equal to 0. Okay? So 2 examples today, and then guess what? We're done the course. Woohoo! Example number 1. So here we have a position vector, and notice the first component is the x. The next component here is the y, or particle that moves in the xy plane. I want you to find the following. So in part A, I'd like you to graph the path of the particle on the interval from 0 to 2. So very typically, the easiest part here is just to make a table of values, in this case of t, and I'll go t 0, 1, and 2. Then I'll have to find the components of both x and y, and once I've found the x and y components, I can then graph it on the coordinate grid. So when x is, when t is 0, if I plug into x, I get 0. I'll do the x's first, right? Then it's 3. 2 squared is 4. What does that leave? 4. 12, I think it is, yeah. And then if I plug in 0 for the y component, I get 4. 1 would be 1 minus 3 is negative 2, plus 4 is 2. And if I plug in 2, 2 cubed is 8. 8 minus 12 is negative 4. And then I think that's just 0. All right. So now looking at this, there's the point 0, comma 4 right here. Here's a point 3, comma 2 right here. And then 12, comma 0 right over there. So I hope you can kind of see that the curve looks something like this. And I'm going to put directional arrows so you can see that the path is traveling towards the east. Okay. The velocity vector at time t equals 1. Yes. So v of t. Right? How do I find velocity? The derivative is 6t of the x component. Yes. And the derivative for the y component, 3t squared minus 6t. Pretty straightforward. And then I want the velocity at time t equals to 1. So yes, I just have to plug in 1. We have 6 times 1 is 6. And then here, 3 times 1 is 3. minus 6, that's just negative 3. So the components of the velocity at time t equals 1, the x component, the x prime component I should say, because it says velocity is 6, and the y prime component is negative 3. How do I find the speed? Well, it's just the square root of the components of the velocity squared. 36 plus 9. That's just root 45, and if you want to simplify to 3 root 5, that's cool, but not required. Okay. Distance traveled. Yes, that's just using the formula. So the total distance traveled would be the integral from, I guess in this case, 0 to 3, the square root of, and I'm going to take the components of the velocity, which would be 6t all squared, and then also 3t squared minus 6t all squared dt. Oops, I should not put the dt inside the square root. Bad notation. Keep it outside. Okay. And then if you're trying to do this by algebra, I'd say please don't. Use the graphing calculator, please, in the FNINT function. Then you can calculate the actual value. Okay, and I won't do it here for you. I'll just tell you the answer. I got 28.583. Okay. Now in part E, I ask you for the time when the particle is at rest. So this is where you're thinking, at rest? Oh, the velocity must equal 0, right? So the components of velocity must equal to 0, okay? And not just the components, all components, okay? So both the x component and the y have to be 0. So all components of velocity have to be equal to 0. So therefore, I'm going to take the x component and make that equal 0. I just get t equals 0. And I'm going to do the same thing with the y component, which would be 3t squared minus 6t. And I'll make that equal 0. And if I can factor this out, I'll notice, and I hope you notice too, that we have t equals 0 and also t equals to 2. But once again, at rest means I need both components to be equal to 0. That would be both components. So therefore, the only answer here, is going to be t is equal to 0. Only answer. Remember, all components. Okay? And then if I want the acceleration vector, no problem. We know that acceleration is just the derivative of velocity, or in this case, the second derivative. So I think if I take the derivative of 6t, it's just 6. And the derivative of 3t squared minus 6t is just 6t minus 6. And then plugging in the value of 2, notice the x component is always the same. And then 6 times 2 minus 6 is also 6. There you go. That's the acceleration vector. And the last part for example number 1, finding the direction of the particle at time t equals 1 when t equals to 2. So 2 separate questions here. I'm really asking for s of 1. Okay. And that means I have to plug it back into the position function above. Where is it? Where is it? Where is it? Yes, 3t squared. So I guess that would be what? 3. And if I plug in 1 for the part, 1 minus 3 is negative 2, plus 4 is 2. So there is s of 1. If I want to find theta, that's just going to be, yes, the arctangent or inverse tangent of the y over the x. You still remember that from last day? Very good. 0.588 radians. Okay. And if you can try the next one yourself, I'd be really happy. Then I don't have to talk. Then you don't have to listen to me. Ooh, y is 0. Nice. And the direction, well, this is going to be straightforward. The arctangent of 0 is just 0. Okay. All right. So I think you have a good idea of what's going on now. Your job is to look at example number 2, and I think you can do it all on your own, because It's just going backwards. This time I'm starting off by giving you the acceleration vector. And then you're going to have to find the velocity and position vector. Thinking integrals. Yeah, integrals. And then answer the questions about speed, about when it goes to rest, and also the direction at a particular value t. Okay? I'm going to ask you to try this yourself first, and then when you're done, come back and check your answers with what I have. But in the meantime, please press pause and try this yourself. So once again, antiderivative exponents, -2 sine t. Don't forget plus c. And I'm going to use c sub 1 here because we're going to have the plus c for the y component. So I just want to make sure that we know that these plus c's are actually different things. I think the other component is just 3 cos t, right? Yeah, plus I'll go c sub 2. You have some initial vectors, so I should be able to plug this in. 0 and 3 is equivalent to, in this case, when I plug in t equals 0, I get c sub 1. And then also over here, I get 3 plus c sub 2, because cosine of 0 is 1. So from here, I can equate the components. So c sub 1 equals to 0. And also c sub 2 happens to be 0. Nice. So therefore, our velocity components are -2 sine t and 3 cosine t. And if I want you to evaluate, which is what I asked you for, pi over 4, sine pi over 4, 3 cosine pi over 4. And yes, we should actually evaluate that. Sine pi over 4 is just root 2 over 2. Same thing with cosine pi over 4. So I'm thinking negative root 2. And this is just 3 root 2 over 2. Done. Did you get that? Clap your hands. Looking at the position vector, that's x of t, so I better do that. The antiderivative here is 2 cosine of t plus, and I'm going to go c sub 3 as a separate constant. And then the antiderivative of 3 cos t is just 3 sine t. And once again, c sub 4. I've got an initial condition here that I can use, 2 root 2 over 2. Which would be what? 2 times cos of 0, that would be 2 plus c3, and then 0 over here would just be c sub 4. So therefore, c sub 3 is 0, and c sub 4 is not. It's root 2 over 2. So therefore, x of t in the component form is just 2 cos t for the x component, and 3 sine t plus root 2 over 2 for the y component of position. And therefore, I can hopefully use, oh, by the way, sometimes we use s, so if you want to use s, that's fine, x. Sometimes it's not so good because that might confuse you with the component x. So let's just use s, sorry about that, and now just s of pi over 4, 2 cosine pi over 4, 3 sine pi over 4 plus root 2 over 2, cosine pi over 4 root 2 over 2, so root 2 over 2 times 2 is root 2, and then 3 root 2 over 2 plus root 2 over 2 is 4 root 2 over 2, which is the same thing as 2 root 2. There you have it. The position vector at time t equals pi over 4. Woohoo! Okay, so now CD, oh, and F. I forgot about F. Speed. Hopefully you know speed. Speed. Right? Take the velocity components, thank you, at pi over 4. Square it. 3 root 2 over 2 squared. What do we get here? Well, that's just root 2. This is what? 3 squared is 9. 9 times 2 over 4. That's 9 halves. So I think 9 halves plus 2 is the same thing as 13 halves. The square root of 13 halves. Right? The time when the particle's at rest? Well, we need now our components for velocity to be equal to 0. So here's our x component of velocity. And if I make that equal 0, then of course t equals to 0, pi, and 2 pi, etc. If I did the same thing with the cosine, or sorry, the y component, that would be 3 cosine of t equals 0. If I solve here, I get pi over 2, 3 pi over 2, and so on. You'll notice that it will never have both the x component and the y component equal to 0 at any time t. So therefore, this particle is, you guessed it, never at rest. Okay? The direction of the particle when t equals pi over 4. Well, direction, that's theta. That's the arctangent of y over x. And the y and x component are from part B, so 2 over root 2, which is just, that's right, 2. 1.107. Ta-da! Okay. And finally, the distance traveled between 0 and 2. Yes, just use the integral formula from 0 to 2. Put in here the components for velocity. Don't forget to square them. dt, and once again, using your graphing calculator, did you get 4.856? Yay! Your notes are now complete, but you still need to practice. So go ahead and please practice. Practice, 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 practice. All right, it's been a pleasure. You are probably sick of my voice, so now you don't have to listen to it anymore. Unless you're going to review and rewatch some of the videos. Oh my goodness. Well, if you do that, I'll see you soon. And if not, thanks for listening.